Welcome to today's webinar, Modeling a Reciprocating Compressor with Low-GWP Refrigerants, brought to you by CONVERGE Science. Thank you for joining us today for this new installment of our webinar series. My name is Matthias Sulis and I am part of the business development team at CONVERGE Science. I will be your host for today's event. I'm glad I can be here with you today and show you how CONVERGE CFD software can be used to model reciprocating compressor with reed valves, as well as other type of compressors like screw, rolling piston, and scrolls. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Vignesvar Ravisakar. Vignesvar is a research engineer on our new application team at CONVERGE Science. He received his bachelor's degrees in mechanical engineering from the Indian Institute of Technology, Varanasi, and his master's degree from the University of Florida, where he worked on a jellyfish model using the immerse boundary method. Without any further delay, I will now pass the ball to Vignesvar. Thank you all.
Hello everyone. Before going into the presentation, I want to give a special thanks to Tecumseh for providing the validation data through their experimental validation and extensive experimental data, so we can be using it for this presentation. And now going into the presentation. So first, before going into the case setup and other details, why do we need CFD for these pumps and compressor applications? So first thing, there are 1D modeling tools available for these pumps and compressors, which actually gives a decent results and approximate calculation for efficiency and the PV curves. However, with more and more complicated compressors, or even if there is any intricate flow development happening, you do need a 3D CFD solver to capture those local phenomena so that we can be getting a very good match on these efficiencies as well as the pressure values. So the main challenges with a 3D CFD solver for these pumps and compressors are you're going to be having too many parts, a complex interface, small gaps, and there's going to be a lot of complex moving geometries. Now, creating a mesh for these complex geometries is going to be really a challenge, especially when you do successfully make a mesh. Since the mesh is going to be moving along with the geometry, it's going to be a big challenge because it's going to create numerical diffusions because of moving meshes. So in that sense, CONVERGE plays a huge role where we are going to be using a cut cell method, which is going to be stationary. And these orthogonal meshes, since it's being stationary, only the boundaries are moving. We are not going to have any of those numerical diffusion. Additionally, we do have an autonomous meshing strategy, which will automatically capture any gradients of velocity, pressure, or temperature, capturing the local flow physics very well. At the same time, we are not going to be wasting any time on pre-processing, creating any meshes. Addition to these, for these compressors and pumps, the major challenge is providing the boundary conditions. CONVERGE has a very good advantage of providing these boundary conditions with a simple table, or even simpler, just providing an engine.in file, for example, in this reciprocating compressor, where you can just create these translator mechanisms pretty easily. We do have a note from Tecumseh acknowledging our advantage in this particular domain. Before going into the next slide, this is a quick view of the reciprocating compressor simulation, which we'll be discussing in most part of this webinar. As you can see, the flow developments have been captured really well, and the valve movements are also being captured really well. So before going into the case of why we need to use CFD specifically for the refrigerant compressors. So one major thing is using an experiment for these is going to be a real challenge. Going on trial and error is going to make it really expensive, and you have a huge amount of uncertainties in boundary conditions. And also we have to intrude devices, which is going to affect your flow field in experimental data. And we also have a limited scope on image capture for these. And as the compressors get more and more complicated, we're going to be having a lot of transient behavior and anisotropy, which can not be captured very well or detailedly studied with an experimental data. However, with CFD, we can be actually study these information really well. And also it's going to have a huge time consumption and cost requirement for building the prototype and building the test rigs. Another major challenge being currently with the environmental concern going on, we are being pushed more and more for low GWP refrigerants. Specifically, that means the global warming potential to be lower and lower. So for that reason, you have to keep changing the refrigerants. So we have to keep doing these tests again and again if we are changing the refrigerants to check if the performance or the behavior is changing a lot. In case of CFD, especially with CONVERGE, just changing the fluid properties can be done in minutes, and then the simulation can be rerun easily without much change in cost. So in today's presentation, what we will be considering is a reciprocating compressor. We are going to be, these reciprocating compressors are run with R404A, which has a GWP of 3900. We are going to be replacing it with 449A, which has a much lower GWP, which is 1200-ish. So what we are going to do is compare the impact on performance, the read valve behavior, and thanks to Tecumseh, we have experimental data which we will be comparing for both these refrigerants. So before going into the CFD, we have to talk a little bit about the experimental parameters, the measurements we have. So first, regarding the test conditions, as I mentioned before, we are using the two refrigerants R404A and 449A. These are the composition for both the refrigerants. The mass percentage has been shown in the table here. And for the test conditions, we are going to be using ARI and ARSHA, and the respective suction pressure, discharge pressure, evaporation temperature, and condensation temperature for these are mentioned here. So which sums up to be 4 different test conditions we will be discussing today. And for the experimental measurements, we have the temperature, pressure, which has been measured in the suction muffler, cylinder bore, cylinder head, and discharge muffler. And also we have the read valve measurements through the strain gauges attached to the discharge as well as the suction read valves. In this particular reciprocating compressor, we have 1 suction valve and 2 discharge valves. The measurement has been done on one of these discharge valves. And for synchronizing these information, the temporal information with the crank position, they have used an encoder. And all of these are shown over here in the images over here. So let's go into the computational domain. So the computational domain was extracted from the CAD geometry. We have a flow starting from the suction inlet, moving up to the discharge outlet, which is marked as I. Regarding the boundary conditions, I'll be going in detail as marked over here. For A, which is the suction muffler inlet, we are imposing a time varying pressure, which is got from the experimental measurements, which then goes into the suction muffler, followed by the suction port, which is marked as B. For both these valves, we are providing a stationary law of wall boundary condition. And then from there, it's going into the suction read valve, which is C. For both the suction read valve and the discharge read valve, we are going to be using a 1D beam FSI model. I'll be discussing about this in more detail in the following slides. From there, it's going into the piston. The piston motion has been provided using the clank slider mechanism, which is marked over here as D. Following that, it's going to go into the discharge port, which is the discharge chamber marked as F, which is again going to be provided with the stationary law of wall boundary condition, followed by the discharge mufflers, which is going to be G and H, which is again going to be stationary law of wall, followed by the discharge pipeline into the outlet I, which is going to be imposed as a constant pressure boundary condition. So now let's go into the detail of the beam model. For the beam model, as I mentioned, we are going to be using a 1D beam model. For this, we are going to be using a 1D Eulerian beam. And FSI as well as the fluid domain are solved explicitly in an explicit manner. And for the grid, as I mentioned before, we are going to be using a Cartesian cut cell method with velocity and temperature based AMR. And for coupling, we are going to be using piezo. And for spatial discretization, we are going to be using a second order momentum and first order turbulence. And for time step the temporal time step, we are going to be using first order implicit. For the properties for R404A and 449A, we are going to be using the CoolProp library, which is available within the Converge Studio, which is the GUI interface of our Converge solver. I'll be talking about this in more detail, how to extract the data from CoolProp within Converge. And for the turbulence model, we will be using RNGK epsilon. And as I mentioned before, for the wall model, we will be using two-layer law of wall. So now into the properties. As I mentioned before, we do have an in-house CoolProp library. So for extracting that, first we will be going into the gas simulation, tabular fluid properties. Once you click on the tabular fluid properties, it opens up this fluid properties configuration, where you will be providing the min max temperature as well as the delta T, which is going to be the increment in which you want the data to be, and the pressure input, again min max as well as the increment values. In this case, example I've shown over here, this is for refrigerant 404A and 449A. We do have a refrigerant 404A as it is in the CoolProp, so we are directly providing that as a composition. In case if you don't have a refrigerant that is directly available, for example, in this case it's 449A, we can directly provide the volume fraction and the respective composition. The CoolProp library will automatically generate the fluid properties, which will automatically get synced with the solver. Next, for providing a boundary condition, something like a piston motion. So we do have an engine.in. We can create an engine.in within our Converge Studio, our GUI interface, where you can be providing the cylinder bore, stroke length, connecting rod, and all these information along with the RPM, and then the respective piston, liner, and head boundary conditions. And then in the piston, in the boundary condition, you can just mention the piston motion. Based on these provided information, the crack slider mechanism will be used, and automatically the piston motion will be calculated during the simulation based on the respective crank angle. And now regarding the FSI, which is the beam model, Converge offer both deformable beam model as well as rigid body. In this particular example, we don't need to use a rigid beam model, rigid body model. We are going to be using a beam model. So I'm not going to talk about the rigid body in this. For the beam, mainly what you're going to be providing is the read profile. And then since it's a 1D beam, you're going to be providing the axis of the 1D beam, the origin, as well as the direction in which the deformations are happening, and number of elements you want to resolve the beam model, and the type of beam, if it is a cantilever or it is attached on both ends. If you have any external loads or initial deflections, you can be providing those. In this case, I don't. And you can also have contact models. In this case, we do have contact modeling. For example, if you see the image over here on the bottom center, we have a discharge reed valve where we have a stopper on the top and we have a seat on the bottom, which restricts the motion of the discharge valve. So the contact constraint can be directly provided as these boundaries, or you can provide the profile of the stopper and plate, which will be used as the contact modeling constraint. You can also add monitoring points on these reed valves if you want to measure the displacement, velocity, and acceleration at a specific location. So before going into the results, I just quickly want to show how the simulation looks like when we have already provided all these boundary conditions correctly. As you can see, the flow is very well predicted using our adaptive meshing. The suction valve as well as the discharge valves are also working fine. And you can also see from this video, the piston motion is also pretty good. So before going again for the results, we will be checking how the grid, autonomous grid refinement works. As you can see here in this cut slices, you can see the AMR is automatically activating the grid refinement around the valves and capturing these local flow really well. This again helps in predicting the valve opening and closing time really well. And again, as stated by Tecumseh over here, due to these autonomous meshing, we don't need to have a really fine mesh over here throughout the simulation, which might make the simulation really expensive. These autonomous meshing will automatically add the mesh wherever it is required and also remove them whenever it is not required, saving a lot of computational time. So let's now go a little bit into the quantitative and qualitative results comparison with the experimental data. Before going into the results, there have been a small modeling of leakage done for this simulation. What I mean by the leakage modeling is generally during in a reciprocating compressor, we do have a small leak between the piston and the cylinder bore. So these leaks can be calculated, can be modeled using a simple orifice flow. So we have added an orifice flow as a UDF so that it can accommodate for these leaks. And as you can see from the results for all these 4 test cases, our results are matching pretty well for the cylinder pressure as it goes along the different crank angles. Let me take one particular plot and explain it in more detail what's actually happening in the physics. If you see the top right, top left plot over here, as you can see, our compression is actually predicted really well. We are having a really good match with our base model with the measured data. And we are able to also predict the oscillations that is happening when there is an expansion starting when the discharge valve opens. And we are having a very small under prediction in the peak value. This might be because of the model we have used for the leak. And also there are some fluctuations observed at the discharge. Since we are using a constant pressure at the discharge, it might be also a reason for this small deviation. Still, we are still under 2% error. So that's pretty good. Another thing we can be noticing in all these plots are the measurement data did observe a fluctuation during the expansion process, and our model is able to capture these fluctuations really well. We do see an offset in the phase. We still need to do a further analysis for further on these fluctuations. Next, if you go into the fluid temperature, as we have included from the suction muffler to the discharge muffler and provided a wall boundary condition, we can see how the fluid temperature goes from the inlet to the outlet, and we do have an measured data for this. For the 4 different test conditions, the results are shown below. We have a very good match with the measured data. And now regarding the valve lift, as you can see, like our valve lift for the suction as well as the discharge matches pretty well. First, we are able to match the valve timing pretty well for both of these cases, as well as we are able to match the amplitude pretty well. So the reason why we are able to do these 2 pretty accurately is because of the leak model, as well as we have provided a very good fluid properties table that matches closely with the experimental data. We do see small fluctuations in the suction valve, which is not captured over here. This is because we have used a 1D beam model. In the following slides, I will be showing an abacus coupled simulation, which will be able to capture these small fluctuations that is happening around 0° crank angle. So the next we have the grid sensitivity study. As you can see from grid 1 to 4, the local flow physics are captured very well even in the coarsest mesh. With further refinement, we are able to capture it in a little bit more detail. However, for most part of it, it's captured really well. And doing a grid refinement study in CONVERGE is pretty easy. All you need to do is change one particular parameter, which is going to be the base grid size. It saves you a lot of time from pre-processing the grids and stuff. So for this particular grid sensitivity study, CONVERGE has a huge advantage over the other competitors. And now if you see the results with the grid sensitivity, as you can see, for all the 4 different grid strategies shown over here, the frequencies are pretty much not changing with any of the grid strategy. However, for the chamber pressure as well as the discharge pressure shown over here, you can see here the amplitude is having some variation with the finer grid. That too, like the variation diminishes as you go from grid 2 to grid 4. So now let's go into the abacus couple simulation. I'm going to briefly show you the case setup for these abacus couple simulation and some simulation results, how it looks like with abacus couple simulation. So for going for the abacus, the main reason why we wanted to do an abacus coupled simulation for this is, assume you don't want to do a 1D beam. You feel the local flow physics will have a huge impact if you include it as a 3D beam model. including abacus coupled simulation will be really useful for those, or not just for this particular compressor. If you have any other particular compressor or pump or any applications where the deformation may be more complicated than a 1D beam, using abacus coupling will be really useful. So for doing that, we have to first turn on the code simulation, which is highlighted on the right. Once you turn it on, you can go to the respective boundary conditions and select the motion type as abacus. In this particular example, I have done abacus coupling only for the suction valve. I have still used a 1D beam model for the discharge valves, just for an example purpose. Once you have selected the motion type as abacus for the suction reed valve, the next part is going to be providing the events when to open and close based on the deflection values. And once you have provided that, you need to be generating an XML file. An XML file is sort of helps in communicating between Converge and Abacus. So this controls how frequently Converge and Abacus will be communicating between each other and what are the information that will be transferred between these two solvers. So mainly, what are the information that's covered in an XML file, which is highlighted on top right over here. Let me use the pointer. So you can see over here, first thing is going to be the simulation time provided as duration, followed by the negotiation method. Negotiation method simply can mean like how frequently Converge and Abacus are going to negotiate with each other, the DT restriction between them. So there are two options. There is min, there is max. In this case, we used max. The difference is going to be if you use min, the lowest DT of the two simulations will be the DT for both the simulations. It's going to be tightly coupled. Generally, it's useful if you want to use an implicit solver. If you don't, then you can be using an explicit with max. Max, what it does is both the solvers will be running with its own DT. The case which is running with a larger DT will wait for the other to reach to the same simulation time so that the information can be transferred between each other. And what do I mean by the information transfer between these two? First, Converge will be providing the pressure forces as well as the location where these pressure forces are measured, which is going to be the triangle information to Abacus. And Abacus is going to use this as a boundary condition to solve for these respective elements in their mesh. Once it is solved, it's going to transfer the displacement value from these elements back to Converge, where Converge will do the extrapolation or interpolation so that it can provide these displacement values to the respective triangles in Converge. I've just shown a screenshot in the bottom to show the Abacus case setup. Again, in this case, we have a contact constraint between the suction reed valve along with the seat, and we do have a stopper in the cylinder bore, as well as there is going to be some contact constraint between the piston. So I had to include all these geometry for providing the contact constraint. Additionally, I provided the piston motion as a boundary condition in Abacus, so that as the piston moves, the constraint will also be changing. So now let's look into the results, how Abacus coupled simulation looks like. The main advantage, as I mentioned, since we are doing a 3D beam model, we should be seeing deformations happening in the other directions, and which we did see in these simulations. As you can see here in the suction valve, which is shown on the in the video on the left, you can see small wiggles happening at the top dead center. So let me go back to the. So you can see small wiggles happening at the top dead center, which is expected from the experimental data. As you can see from the plot on the bottom left, there are small wiggles expected at zero crank angle, and which was not captured by the 1D beam model, which was captured really well with this Abacus coupled simulation. So that's the main aspect of the reciprocating compressor. So the rest part of this webinar, we will be covering about the different types of compressors and pumps where using Converge can play a huge advantage. So the first I'm going to be discussing is a twin dry screw compressor. So as you all know, the major challenge with the twin screw compressor is the complicated geometry and how the chamber volume keeps changing here. It will be a huge challenge to create a mesh for these, and a moving mesh will again cause a numerical diffusion. Since Converge uses a stationary Cartesian cut cell method, these numerical diffusions of the moving mesh won't be present, and also the cursor will automatically take care of conserving the volume in the chamber, which still gives a good results. At the same time, with the automated meshing, we still will be able to refine where the flows need to be defined based on the gradients, and we can capture the local flow physics. There are 1D tools that can actually give an approximate results for based on the chamber volume changing. CONVERGE also offers a volume and area calculator for these 1D calculations, addition to the 3D CFD using their GUI tools. These things can also be used for a simplified 1D calculation if you are doing a design approximation or design a simple initial design validation. Now going into the case, for this particular example, we are going to be taking a 3-5 type twin screw compressor, which is a dry compressor. And we are going to be validating the results with City University of London. And mainly the things we are going to be validating is going to be the mass flow rate, power, and the outflow pressure. One of the major challenges for these simulation is going to be, there is going to be a leakage from a higher pressure to a lower pressure chamber between the two rotors, as well as between the rotor and the housing. To model this, we are going to be using a gap modeling, which is technically we are going to add a momentum sink by adding a porous media, which will resolve, so instead of resolving these small gaps, we're going to be modeling those for the leakage. As you can see, like with this grid refinement study on the plots shown below, from grid 4 and above, we are able to have a really good match with the flow rate as well as with the power, and also at the discharge temperature. The result seems to be converged really well. Confirming the grid, the gap modeling is also working pretty well. The next is going to be the rolling piston compressor. So before going into the rolling piston compressor, many people might not know what it is. So let me show an animation of how it works. So we have a stationary cylinder as well as a rolling piston which is inscribed in it. It has a sort of a rotating translating motion, which also causes a translating motion of the vane, which is shown on the top over here. And in this vane sort of separates the suction from the discharge. And again, in this case, for the discharge, we are having a reed valve over here. Providing boundary conditions for these complicated boundary conditions might be a huge challenge. However, with CONVERGE, all you need to do is provide a table separately for these rolling pistons and a translation motion table for this vanes. It will automatically take care for the simulation, which makes it really easy. And for this particular example, we are going to be comparing the efficiency as well as the chamber pressure at 3600 RPM. And for the refrigerant, we are going to be using R134A. Again, we are going to be using the CoolProp library available within CONVERGE for creating the properties for this. As I mentioned before, the motion of the sliding vane as well as the rolling ring has been provided using just a table. And as you can see from the efficiency, we are having a pretty good match on the efficiency. We do see some drop compared to the measured data. This is because we haven't modeled the radial leak happening. And again, you can see here from the pressure versus volume, which we are having a very good match. And specifically for grid 4, 5, and 6, we are having the grid convergence have been established. Again, the image on the video on the bottom shows how well the grid autonomous grid is doing good. It's able to capture all the local physics very well, at the same time saving a lot of cost from pre-processing. So the next we will be considering is the claw vacuum pump. The major challenge for this claw vacuum pump is going to be the complex geometry, how the motion is being captured. Again, we can be providing a simple rotation just with one single variable of RPM. The main thing about the claw vacuum pump is the dead volumes. Again, CONVERGE offers both 3D CFD as well as a simple tools for area volume calculators with respect to crank angle using our GUI interface, which can again help for a simple 1D analysis for an early stage of designing. In this particular example, like our reciprocating compressor, we have an extensive computational domain, we have an inflow where we provide the pressure and temperature. We have a ball valve angle, which controls the suction pressure, which goes into the claw pump. And then we have the discharge, which again goes into the discharge muffler into the outlet. And as you can see from the pressure volume over here, we are able to capture it really well with the measured data. The next we are going to be considering is another reciprocating compressor. The major difference of this reciprocating compressor compared to the main case we considered before is how the stoppers are for the suction and the discharge valve. Let me play the video over here to show you that. First, for the suction, we don't have any stopper in the cylinder domain, so it doesn't have any restrictions, so it can have like a lot of deformation. And for the discharge, instead of having a stationary stopper, we are going to be having a dampener plate. We are going to be having a damper plate, which is again a beam. So for both the suction, discharge, as well as the damper plate, we are going to be using a 1D beam model. And as you can see here, the beam contact is also captured really well, and the deformation of the damper plate and the discharge valve is also captured really well. And again, the AMR is doing its work on its own, saving us a lot of time and computational cost. And when we compare the validation data, we have a very good match for the normalized pressure. We do see some offset in the suction valve lift as well as the discharge valve lift. This is because we haven't included the leakage between the piston and the cylinder bore in this particular example, like we did in our first reciprocating compressor case. By including those, we will be able to match the timing really well for these cases. As you can see, except the grid A0, rest of the grid seems to have converged and don't show too much sensitivity on the valve opening timing. And next, we are going to be discuss about a scroll compressor. So let me show a video of what a scroll compressor is. Again, this is one of the complicated geometries which Converge can easily handle because of its Cartesian mesh and providing a boundary condition just with a table. And again, we are having a reed valve over here at the discharge. For the refrigerant, again, we are going to be using R134A. Again, we got this using the CoolProp library from Converge itself. These are mainly used for AC applications. And in this particular example, the main leakages are expected to happen radially between the moving scroll and the stationary scroll, as well as the axial leak that is happening between the housing and the scrolls. For the axial leak, we have sealed off completely except where the discharge valve is, so that the discharge valve can open whenever there is a pressure difference. We haven't modeled any radial leak in this case, so there might be a small discrepancy in the results because of that. And most of these compressors are sealed off in the axial direction using an oil lubrication. This in turn will affect the valve opening because of the surface tension of the oil. The reed valve doesn't open immediately. There is going to be some delay. To accommodate for that, we have applied an initial load of 15 Newton in the reed valve, which will again we'll be seeing as we discuss the results. We'll be seeing their importance. So first, let us go and discuss about the pressure. As you can see, we are able to capture the pressure really well. We do a little bit overestimate on the pressure amplitude. This is because we haven't modeled the radial leak. If we did include that aspect, the pressure capture will be almost perfect. One thing to notice over here is we are able to capture the oscillations during the discharge really well, which was also seen in the experimental data. Now, if you move to the valve lift, as you can see, due to the prescribed initial load in the reed valve, the valve opens in a pretty sharp slope, which matches really well with our experimental data. And you can see here for the experimental data, the measurements are done using an eddy current sensor, and the measurements are only done after the measurement starts only after 1.4 mm of lift. So that's the reason we are seeing the experimental data to be a little bit of choppy. So as you can see, our valve lift is predicted really well along with the amplitude. However, if you see the closing of the valve is, we are having a much faster close compared to the experimental data. As I mentioned before, there is going to be oil lubrication present over here, which is going to restrict the valve closing. Since we did provide a prescribed motion for only the opening, we are having a good match there, and we are going to have a lag in that. If we include the oil lubrication in this, we will be able to have a very good prediction on the valve closing too. And the final compressor we are going to be discussing is a rotary spool compressor. So before going into the results, again, I'll be explaining a little bit more detail on the geometry. So we have a vane over here, which actually sort on two ends, which actually translate outward due to the centrifugal effect, which separates the chamber into three different volumes. As you can see here, we have a suction volume over here, and then this vane separates this into the compression, and then we have a discharge over here. We have three separate poppet valves over here, which opens when the vanes come in contact. As you can see, we have used refrigerant again, R134A, again using our extensive fluid properties library. And again, providing a complicated motion like rotating as well as the translation motion is pretty easy with CONVERGE. Just with one table, we can be doing this. And again, for the modeling the gap between the vane and the housing, as well as vane and the poppet valves, we have used gap model. If you see the power as well as the mass flow rate comparison, we have a very good prediction with the experimental data. And finally, the additional capabilities, which I didn't show in any of these compressors, are we have an extensive multi-phase solver. So if you have any two-phase screw compressor, which you need to perform a CFD, or you have any specific lubrication for sealing off, or even a condensation aspect, we have a very good view of solver for these applications. Additionally, we can also be doing a 3D conjugate heat transfer, which we haven't discussed over here. Along with the super cycling, we can be accounting for the difference in the time scale in the two different solid as well as the fluid simulation. Additionally, we have UDF capabilities for including a lot more functionality. For example, in this particular spool compressor, we tried to separate the region IDs for the inlet, compression, as well as the discharge. As you can see here, we have flagged the region ID over here. Based on a UDF, we are able to clearly separate the cells, which is part of the compression inlet as well as the discharge. These things will generally be really useful for creating a PV diagram. And we do have a hands-on support team that provides the end-to-end customer support, which can help you with training the engineers for engineering team. And even for any project or particular example you need to be setting it up, you can contact us. We can help you with it. Or even if you have any particular properties you can't find it in the library, you can again contact us. We have an extensive list. We can again help you with that. To conclude the presentation, we did a fully coupled solid fluid simulation with autonomous meshing. We have seen how well the results matched for the cylinder pressure, temperature, and also how the temperature varies along from the suction to the discharge match really well with the measurement data. We did see pressure fluctuation at the discharge muffler and suction muffler, which need furthermore analysis. And we also saw some fluctuations during the expansion, which was captured by both the model as well as the experiment. We need to do a further analysis on that. And again, for the boundary conditions, we directly provided the temperature boundaries from the experimental data. Instead, we can be doing a complete CHD, which might give a better match on the temperatures. Thank you.